So today we are going to solve Leetcode 802, that is find eventual saved states. So in this question we are given a directed graph of n nodes, and this graph is represented in a 2D array where graph I represents all the adjacent nodes. So by this I meant to say this is our graph array, and if I'm saying at 0th index we are having value as 1 and 2, so we can see in the diagram that 0 node is having two outward edges which are going to 1 and 2. So this is how each and every index represents the outgoing edges from every node. So now let's see how we can check all the safe nodes in the question, because we have to return the array containing all the safe nodes of this graph. So firstly, let's try to understand what is safe node and what is terminal node as well. So as we can see in this diagram very clearly that these two are the nodes, 6 and 5 are the nodes with no outgoing edges, and this is what we refers to as terminal node. So if we are going to check in our question, we can see that terminal node is a node if there is no outgoing edges. And what is a safe node? A node is said to be safe if every possible path starting from that node leads to the terminal node. So we can see in this diagram, let's say this one, 4th node. So we can see there is only one outgoing edge, and that is going to terminal node, that is 5th one. So what is terminal node? Terminal node is a node with no outgoing edges, and safe node is a node where all the outgoing edges are directed to terminal node or safe node. So now we are clear with these two concepts. So we have to check all the terminal and safe node in the given graph. So by looking at this graph, I can say that 6 is the terminal node. So fine, because the outgoing edge count is 0. Then 5th is also a terminal node because its outgoing edge count is also 0. Now if I'm going to check the edges which are coming towards 5, that is 2 and 4. So I can see that 4 is having only one outgoing edge, and that is going to terminal node. So this is also a safe node. So till now what we got? 6, 5 and 4 are safe nodes and terminal node. Now let's see the next node which is coming towards 5 or connected with 5, that is 2. So we can see 2 is having one outgoing edge. So this is also going to terminal node, and that's why 2 is also a safe node. Now I can see that 2 is having two incoming edges, that is 1 and 0, right? 2 is having 2 in degrees, and these two in degrees are because of these two edges which are coming from 0 and 1. So if I want to check whether 0 is a safe node or not, so I again have to check the outgoing edges from the 0. So I can see that one edge is going to 2 and next edge is going to 1. So the one edge which is going to 2, it's fine because we just checked that 2 is a safe node. So fine, this one is fine. But the next one which is going to 1, for that I need to check that node 1 is also safe or not, right? So for that what I have to do, I have to again check all the outgoing edges of 1. So if I'm going to check outgoing edges of 1, 1 is going to 2, which is fine because 2 is a safe node. But the next one is going to 3. So now I have to check whether 3 is a safe node or not. Then I'm going to check 3's outgoing edge, that is going to 0. Now I know that I already visited 0. So I can see clearly that this is forming a sort of cyclic graph, right? This is forming a cycle. Now if I am going to enter this loop, I won't be able to ever get out of this cyclic loop and reach a terminal node. But in the question it is given that we have to make sure that the safe nodes are the nodes whose outgoing edges are going to safe node or terminal node. But in this case, if I am going to enter any cycle, I won't be able to ever reach any of the terminal node. So after analyzing this whole graph, I came to a conclusion that first thing is I have to check I should not enter in any sort of cycle, right? And second thing that I realized is if I'm not entering the cycle, rest of the edges are safe, right? Rest of the edges are safe. So what's the most important thing we analyzed after going through this whole diagram? The most important thing is that we need to eradicate all those nodes from our answer which are included in a cycle, right? They won't be a part of our answer. So if you are familiar with this type of question, then you must be already knowing that algorithm. But in BFS traversal, there is an algorithm named as Kahn's algorithm. And Kahn's algorithm is having some similar concepts. So we will be solving this question using Kahn's algorithm. Now we know this is a graph and this can be traversed by two approaches, that is BFS and TFS. So as we already know the key points that we have to focus on, that is the cycle and the number of in degree and out degree of the edges, on the basis of that, today I am going to solve this question using BFS, and that even Kahn's algorithm. So what is Kahn's algorithm and how it works? So firstly, Kahn's algorithm focuses on the in degree of all the edges. So if I'm saying this is a node, this node's in degree is 0, right? 6 in degree is 0, 4's in degree is also 0, 5's in degree is 2, and this is how we calculate in degree, the number of incoming edges towards that node. So Kahn's algorithm keeps a track of in degree. Secondly, what it does is once the in degree of any node reaches 0, it simply deletes it from the graph and stores it in a queue. After that, what it does is it travels through that queue and then delete its outgoing edges. So if I'm saying 4 is one of the node which is in my queue, it will eradicate this node, and after eradicating its nodes, what it will check, the node towards which it was going, its in degree is 0 or not. If its in degree becomes 0, then again it will insert it in the queue, and then the same process continues to the point where all the possible nodes with 0 in degrees are achieved. And one of the benefit of Kahn's algorithm is it eradicates the nodes which are a part of any cycle. So let's see how we can solve this question using Kahn's algorithm. So as I already said, it keeps track of in degree and store the nodes with in degree equivalent to 0 in a queue. So like we already know, as of now the current status of the node is 6 is having 0 in degree and 4 is having 0 in degree and 5 is having 2 and 2 is having also 2, 0 is having 1 in degree, 1 is having 1 in degree, and 3 is also having 1 in degree. So on the basis of this status, what will be the Q value? Q will be having 4 and 6 right now. So what I am saying, now pop this 4 from your Q. So I popped it. So now what we have to check, we have to delete its outgoing edge. So I'll delete this. Now I'm saying check the in degree of 5. So as this one is removed, so in degree of 5 will become 2 minus 1, that is 1, right? This will become 1. So is this equivalent to 0? Then no. Then I can't push 5. But now if I'm going to see this diagram, what I'm able to see is even if I'm going to pop 6 out of this queue, I won't be able to traverse this part of the graph. This part of the graph. Why? Because this part was connected with this edge which I just deleted. So now I won't be able to go to 5 and 2. But previously when I analyzed this graph, I know that 2 and 5 are also a safe node and they are a part of our answer. Then how we are going to utilize this Kahn's algorithm? Now as we know that Kahn's algorithm focuses on the in degree of nodes. But according to question, what we were focusing on for checking the safe node? For checking the safe node, we were focusing on the out degree, right? Out degree, because we said if the node is having out degree equivalent to 0, it is a terminal node, right? And then we have to check if it is having out degree, then it should be going to terminal node. So we were somehow focusing on out degree, but Kahn's algorithm focuses on in degree. So now how we can just utilize this Kahn's algorithm for our this question? But if I say that inverse of out degree is equivalent to in degree, right? If I'm saying that 4 is having out degree or the edge towards 5, so if I'm going to reverse it like this will become in degree, right? Now the outgoing edge is reversed. So now I can utilize the in degree part. So what I'm trying to say is if I'm going to reverse the whole graph, I can still utilize Kahn's algorithm. Now the Kahn's algorithm is somehow going to be utilized in our case for our out degree concept. Reverse of in degree is going to be out degree. That's why we are going to reverse the whole graph so that we can utilize Kahn's algorithm and travel whole graph without leaving any of the edge. So let's try to dry run this algorithm on the reverse graph. So let me firstly draw the reverse graph. So this is our reverse graph. You can see I simply reversed all the edges. So now let's try to utilize our Kahn's algorithm. So let me just write the in degrees first. So still the in degree of 6 is 0. The in degree of 4 becomes 1 because now this is being reversed. Now the in degree of 5 is 0. In degree of 2 becomes 1. In degree of 0 becomes 2. In degree of 1 becomes 2. In degree of 3 becomes 1. So this is the in degree status. Now let's create a queue. So in our queue, firstly we will push all those nodes which are having in degree equivalent to 0. So 5 and 6. Now I am saying pop the element from your queue and check all its adjacent node. So what are the adjacent node of 5? That is 4 and 2. Now I am saying delete the outgoing edge of these two nodes. So firstly let's remove this one. So if I am going to remove this one, what will be the in degree of 4? It will become 0. Right? It will become 0. So what I am saying, just insert it in your queue. And let me just remove this 5 from our queue so that it will be more clear, because we are going to have a separate list for our answers. So as soon as I pop this element from our queue, I will insert it in a different list and mark it as safe. So this will be our answer list. So what I did, I removed this outgoing edge of 5, and as soon as the in degree of 4 becomes 0, I inserted it in the queue. Now what I'm saying, okay, this is done. So now check this one. Delete this outgoing edge as well. So I delete this outgoing edge as well. And now I have to check what's the in degree of 2. So now I can see the in degree of 2 will become 0. So I will insert that as well in my queue. Now the adjacent node of this node is done. So what I'm going, pop next element from our queue. So again I will be popping 6 from our queue, right? I will be popping 6 from our queue. And what are the adjacent node of 6? Nothing. So what I will do? Nothing. I will simply insert 6 in the answer array and I will go to next element. I will pop 4. So now let's check the adjacent node of 4. But I know that I already removed this edge. So now adjacent node of 4 are also nothing. I simply insert 4 in my answer. Now I will pop 2. So now I have to check the adjacent node of 2. So adjacent node of 2 are, or the outgoing edges from 2 are this 1 and 0, right? So what I am saying, delete firstly 1. So if I am going to delete this one, this edge, what will be the degree in degree of 1, node 1? It will become 2 minus 1, that is 1. But this is not equivalent to 2, right? This is not equivalent to 2. So what I am saying, fine, proceed to next element. So next element is 0. So now delete this outgoing edge. So I deleted this outgoing edge. Once I delete this outgoing edge, what will be the in degree of 0? It will become 1, which is also not equivalent to 0. So I will won't insert this as well in my queue. But this as well in my queue. Now I am done with all the outgoing edges of 2, right? I am done with all the outgoing edges of all the elements that were in my queue, and now my queue is also empty. I hadn't deleted these elements, but as soon as I was just putting that dash, that was referring to that I am popping those elements. So now I can see my queue is empty and my answer is having 5, 6, 4, 2. So this is my answer array. I will sort it and I will return it. So this is how Kahn's algorithm works. Firstly, it will create a queue which will store all the nodes whose in degree are equivalent to 0. And after that, it will check all the outgoing edges from that node and delete it one by one. And if the in degree is becoming equivalent to 0, then it is going to push that node in our queue and again check its outgoing edges. And this will be continuously happening to the point where our queue is empty. After this, we can see very clearly what all nodes are left. We can see 3 is left, 1 is left, and 0 is left. And we know that these are a part of cycle. So this is how Kahn's algorithm works and why it is beneficial. Because it simply eradicates all the nodes which are a part of any cycle. So we won't end up in that loop or in a cycle, so that we won't be able to reach our terminal node. That's why we choose Kahn's algorithm to solve this question. And as we were aware that we are focusing on out degree and Kahn's algorithm focuses on in degree, that's why we reversed our graph. So I hope till here everything is clear. So now let's code this whole solution. So the first thing is we want length of our graph. Now there will be a list with all the in degrees, because we know that Kahn's algorithm focuses on in degree. Then there will be an adjacency list which will take care of all the outgoing edges, because we will be deleting them, right? We will be traversing them when we are popping it from our queue. So this will store all the adjacent nodes. Now let's fill it, and for that we will run a for loop, and inside that we will have another for loop for our nodes. So I'm saying that add all the adjacent node of this node in this index, at this index, and increase the in degree by 1, right? In degrees will also be increased because these are adjacent node, or the outgoing edges are going to these nodes. So the in degree of this node will be increased. If I'm saying 0 is a node and there are two outgoing edges, that is this one which is going to 1 and this one which is going to 2, so the in degree of 1 and 2 is going to be increased by 1. This is what we are doing and saving here. So after this, what we needed? We needed a DQ, right? We needed a DQ for storing all the nodes with in degree equivalent to 0. So now let's run a loop in which we will check the in degrees. So if in degree I is equivalent to 0, then q dot append I, and then there will be a array which I showed you in the diagram where we were pushing our answers, this one 5 6 4 2, this array. For that we will create an array. By default we will keep our value as false for all the n indexes. Now let's run through our queue, and what I am doing, I am popping firstly the element from the queue, then I am marking that node as safe in our answer. Now I'm going to visit all the neighbors. So for neighbors in adjacent node, I will decrease their in degrees, or I will delete the outgoing edge, that will be minus equivalent to 1. And after removing that outgoing edge, what I'm going to check? I'm going to check if this value is equivalent to 0, right? I'm saying if this value is equivalent to 0, then q dot append this node, right? And once I'll step out of this loop, what I'm saying is save nodes. This is an empty list. What I'm going to do, for I in range n, if safe of I, that means if the value is true, if that node is true, then save nodes dot append I. So in this manner our values will be sorted and will be inserted in a new array, and then we will return that new array as our answer. So this was the whole code. Let's try to run this code. There is a typo. Oh, this is range. I wrote graph. Save nodes is not okay. The code works fine. We can see it beats 64%. So now let's see what's the time complexity. So time complexity of this whole algorithm will be somewhat around big O of m plus n, where m is the number of edges and n is the number of nodes. So like we will take big O of m time for initializing that adjacency list, then big O of n time for initializing our in degree list, then we are traversing through the queue and we are pushing elements into it and performing operations, then we are iterating. Then once we pop the element from queue, we iterate over its neighbor, that will again take big O of m time, and after that we are pushing elements in queue, so that will also take time. So overall time complexity will be big O of m plus. This big O of m plus n will be our time complexity, and space complexity will also be equivalent to big O of m plus n. Why? Because firstly we are having big O of m for that adjacency list and big O of n for in degree list, and then we are having our queue, which in worst case will be equivalent to big O of n. So for that reason, and then we are having our safe array which was storing these values, right? So for that, the time complexity and space complexity both will be equivalent to big O of m plus n. So this was the time complexity analysis and the whole solution for this question, and I hope this video was useful. And if you really find this video helpful, then you can like this video, subscribe my channel, and I will soon come up with few more videos. And thanks for watching.